Okay, and the last special type of question I wanted to show you today is a specific heat capacity mixing question. Now, I've never seen one of these on an exam paper, so it's unlikely you'll get it, but it's just a little thing to know the trick to these ones. So I think it's probably worth you having seen it before your exam. So in this question, we've got 100 grams of brass and it's heated to this temperature. And then it's being put in water, a kilogram of water at this temperature. And so obviously energy is going to pass from the brass to the water because the brass is hotter than the water. And then it's going to stop moving when the brass and the water are at the same temperature. And we're trying to work out what that temperature is. Okay, so it's obviously the specific heat capacity formula, and we are assuming that the water's not going to get to 100 degrees. It's not going to get to its boiling point. Right, so we've got the brass and we've got the water. And we've got the masses of both, and we've got the specific heat capacities of both, or rather, this I would provide this if I was in the classroom. And so the key to this is the change in temperature. The brass is starting at 150 and it's going to cool down. So we don't know what the final temperature is, but its initial temperature was 150 degrees C. And then the water is starting at 15 degrees and heating up. So again, we don't know what its final temperature is, but we know it's the same as the brass. Remember, they stop changing temperature when they're in thermal equilibrium, when they've got the same temperature. So change in temperature of the water, the final temperature minus the initial temperature. Okay. So I might just ditch the subscript there just to make things a little bit neater. So the change in temperature of the brass, I'm just going to use T for the final temperature. And over here, same thing. Right, so let's do the brass first. Actually, I'm changing my mind. Let's do the water first. The energy that the water's going to gain is going to be 1 times 1,200 times, and then T minus 15. And so the brass, the change in energy of the brass is going to be 0.1 times 380 times T minus 150. Okay, now here's the key. Here's the key to the whole thing. This number is positive. The water's gaining energy. And this number is negative because the brass is losing energy. Let's just say the number's 10. So the water is gaining 10 joules. So this number would be 10. And the brass would be losing 10 joules. So this number would be minus 10. Now, 10 does not equal minus 10. 10 equals minus times minus 10. And so when we're obviously going to put something equal to something here, but we need to introduce a minus sign. So as I've just said, the energy gained by the water here let's just say that was 10 and this was minus 10. So this is minus 1 times that. And I haven't really done this very well because you can't fit it in. So I'm just going to have to write the whole thing out again underneath. So just pause for 1 second. Okay, there it is. So the water is gaining energy. How much? It's going to be the same size as what the brass is losing. Okay, this is now straightforward maths, very boring, takes a long time, but it is just solve it to find T. And so there it is, and it comes out as 16 degrees C to 2 sig fig. So we've put 100 grams, so imagine like a 100 gram mass that you have at school, one of them of brass at 150 degrees C, and we put it into, think about like a litre of orange juice, that's a normal big orange juice carton, that much water, and the water was at 15 degrees C and it's only gone up to 16 degrees C. And that's because water is, why is water such a good coolant? Because it has such a high specific heat capacity. Because the water needs 4,200 joules to raise 1 kilogram of it by 1 degree. That means, look at that, it took a huge amount of energy off the brass. The brass cooled down a lot and the water only went up by 1 degree. So water is a very, very good coolant.